Thanks. Nice being here. As James already indicated, this is kind of partly a talk on a paper we wrote in 2020 with one of my students, Bastian, mostly, and quite a few other students. And that's kind of a bit the story of the paper. For me, all of the good papers I wrote always start with rejection first. So this was reject from PLDI in 2020, and then we published this at ICP 2020, and since then this actually has been picked up as a research highlight by SIGPLAN. And if you manage to get a copy of the communication of the ACM this month, you will find actually a version of this paper as it's called a research highlight, which is really nice to see when you have another colleague commenting on why this paper is so cool, right? When prior to this, reviewers just tell you how uncreative and unimaginative you are.
And if your head wasn't already big enough.
Okay. But what I want to talk about today is to a certain extent what we did in this work, and then how we now think about bringing some of these aspects into practice. So we have kind of this nice academic story, right? But nobody in practice actually cares about what we have done in this work, right? So there's a lot of cool stuff in there explaining people how to do things properly, and then everyone is like, oh, let's ignore this and do it different. Okay. So how might we change this? Precursor to this actually is, and I put these two colleagues up there, Elko Visser and Richard Bird, who both passed away last year, like very kind of big names in our field. And I've never met them in person, but they've both very much inspired my career and parts of this work. So Richard Bird has done a lot in the 80s on kind of expressing or thinking about how to structure programs kind of in an algebraic sense and rewrite them and change them, right? And then Elko Visser actually, particular to the type of work we're going to talk about, done a lot of work on kind of rewriting, language benches, that sort of stuff. Okay. So the paper is called, or the paper as we called it was called Achieving High Performance the Functional Way, right? But this was kind of, we wanted to express high performance optimizations as what we call rewrite strategies. Okay. And that has kind of two components. The one being high performance, and the other one is kind of what are these rewrite strategies and how do we get there, right? So what do I mean when I say high performance and how do we care, right? This is now a fairly outdated tweet from like 2020, where someone was saying like, holy crap, it costs $250,000 to train a large language model, okay? And actually, if you turn this into CO2 emissions, then it costs kind of the amount of CO2, which is equivalent of driving a car like from the northern tip of Norway to South Africa to train this one large language model. Okay. So when I talk about high performance, I talk about like optimizing these type of computations that take an incredibly amount of energy, money, right, and time, right? If we wouldn't have the efficiency that we see today with GPUs and people actually tuning the code for it, these large language models just purely wouldn't exist, right? They would not be able to train it for us. So how do we achieve this performance traditionally? And that's what people at OpenAI do currently, right? They just write fast code. Again, they never get it wrong. And it's always efficient. And then the next hardware generation comes along and they start from scratch, right? Or maybe they now use ChatGPT to guess a version of it, okay? But they're trying to use a lower level language, like here this NVIDIA CUDA, right, which is a language to target GPUs from NVIDIA. And while the code on the left, you might still kind of roughly try to understand what this is doing. This is matrix multiply, right? What people actually write is much more the type of code that we see here on the right-hand side, okay, which is so small that you can't even try to read it, right? But you can see just by the depths of nesting, right, that there's a very integrated description of which threads will at which point in time access which piece of memory to then do which type of computation, okay? That means the code explodes, right? I mean, the size of the code is not necessarily a good indicator anyway, but the complexity increases, like ridiculous, right? I mean, understanding what this stuff does and that stuff still does the same as that stuff, that's really hard, okay? But it hugely pays off, right? So if you do these efforts manually, you get not just one, but often 2 or 3 orders of magnitude of performance difference, okay? So people spend these efforts currently. So to address this, a couple of years, there's been kind of a trend published by some research colleagues who have started to think about, okay, what is one way to design compilers and languages in a way where we kind of decouple this performance aspect in a better way from the expression of functional, like the functional correctness aspects. And they come up with this idea of saying like, okay, we can just describe our algorithm, right, in a kind of fairly high-level-y way, okay, where we describe maybe matrix multiplication, but we don't say really how this is going to be executed. And then we have a separate program, a separate description, which they call a schedule, which they see as a recipe to tell the compiler how to transform and optimize this program, right? How to schedule it, right? In which order the instruction should be performed. And then you give to a compiler both of these parts, functional description and schedule, and the compiler combines them together, crunch, 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 right? And then comes out fast code. That's the idea. And that is, for example, what here this TVM framework is doing, which is a popular deep learning framework, right? Where you describe these computations and then you describe the schedule. And the idea is that you should only change the schedule and you keep the computation description the same, right? And that increases portability, comes new hardware architecture along. We only have to change the schedule. We can keep the computation around, but you get the same performance improvements, okay? So that's the rough idea. James.
So what's the comparative, both performance and also actual code generation compared to the manual version? I mean, comparable within an order of magnitude?
For these things.
Yeah, for these things.
Right. So these things are used in production. Like, for example, there's like, besides this TVM thing, right, that is their way to describe computations, right? There are also other things, particularly there's a system called Halide. Okay, and if you have an Android phone, then this will actually power your computational camera. And that is like a huge success story of a domain-specific language that has made it into production because they had this idea of these schedules. Okay, and that means engineers at Google and Adobe, they write these schedules rather than writing the low-hand code themselves. Mm-hmm. Okay, so in certain domains, this idea has kind of reached the level where people say this is better than for prototyping and reaching code than actually writing the code manually. Okay. Right. So I already talked about Halide as this kind of compiler in the image processing domain, right? They have the same idea. Here's another example of one of these schedules. Okay. And I want to highlight a couple of kind of problems we see with this. Okay. So one of the problems, if we zoom into one of these aspects, right, is that these program and the schedule, right, the functional description and the performance description, right, they really blend into each other. They're always written together, right? So this neat, clean separation that you might expect, that means, oh, we can maybe reuse the schedule for other programs, okay, or something like this. That's really not possible. And that starts already with that they use the same identifiers across boundaries, for example, right? So in some sense, these are not two descriptions. This is just one description separated by a virtual line. So that hinders really kind of reuse, that you can say, oh, these abstractions that I might have built in the schedule, right? So that I have a certain type of how I change my code that I reuse this to similar computations, that really gets a bit hairy. A lot of these instructions you see in the schedule, right? So in this description of how the compiler should optimize this program, right? Some of them are really intuitive. So I have an intuition what it says when it says unroll, and I think about a loop. So as a compiler engineer, I know what it means to unroll a loop, but I have no clue what this update actually means. And if you look up the API call, the API description, this will not really be helpful, okay? And the underlying reason here is that these is kind of a fixed set of predetermined operations that the compiler engineers kind of expose to an expert and say, we think this way about computational optimizations, so please adopt this language and kind of follow us, right? You might even say like this unrolling, right? There is no loop in the original program. What are they talking about, right? So there's really a semantic gap to a certain extent between these schedules and the description, right? So that means it's really hard to understand these schedules, right? And then I mentioned this already, this is only built with kind of a fixed set of operations, right? So meaning we have, like, I don't know, here, splitting of loops, unrolling of loops, right? But if you come with a new great optimization on your hardware architecture comes along, you have to change the entire compiler and then expose this new primitive, right? So it's like extending the scheduling language or scheduling API is a massive undertaking. So we are lacking kind of extensibility. Okay, so and like we started back then and said like we should somehow think about this more principled, right? And we should understand these schedulings really as a first-class programming language and not just as an API, a Python API exposed by some compiler. And that's what kind of spawned out kind of our work. Okay. So in the ICFP 2020 paper, we essentially followed a similar setup that we say we have a high-level program that is written in a functional language that uses kind of map-reduce style constructs to express parallelism. That's some work we had kind of done before. And then we added this optimization strategy language we call Elevate, which is based on Elko Visser's ideas from Stratego, which is a way to describe program transformation in a composable way, okay? And in this way, we can describe something like the matrix multiplication top left with like map-reduce style primitives. And then at the top right, we can build a kind of description that the compiler will follow how to optimize this matrix multiplication. But this thing at the top right, like none of these elements in there, like the tiling or the splitting, none of this is a built-in primitive. They're all just built as compositions of rewrite rules. So you control the application of rules that change the program. And you then build these kind of schedule or the strategy, as we call it, in the top right, just kind of as a program itself that transposes step by step the computational description. Okay, that's the basic idea. And that has some advantages, right? So from the compiler perspective, that makes now the compiler design much more straightforward because the compiler is not making any optimization decisions anymore, right? The schedule perfectly tells you how to transform and change the program. Once we have done this, we just generate low-level code by translating like a for loop into the proper for loop bit in CUDA and so on. But we don't make any kind of optimizations at that stage anymore, right? So the compiler becomes a much more straightforward piece of engineering. The key idea for Elevate, following kind of the ideas of Stratego, is that you think about a strategy, a program transformation, as a function with a certain type. Okay, so you think of this as a function that takes a program representation, let's say like an AST or something like this, as a data structure, right, as its input, and then it gives you back a rewrite result, which means either I have successfully rewritten this program, here's the new version, or I fail to rewrite this program, okay? So in this kind of monetically looking type allows then to define combinators who essentially say, oh, if I have two of these strategies, why don't I apply the first one? If the first one succeeds, then I just take the rewritten version and then I apply the second one. If the first one fails, then my composition fails as well. Okay, so that means you can define these compositions who all have the same type again, and then you essentially end up with a nice composable way to describe these program transformations. One crucial other aspect that we have is what we call traversals, and that is a way to describe kind of program locations also in a compositional way. So we can describe, for example, to say you can do a top-down traversal over your AST and try to find, for example, the first point in your program where a certain strategy applies. And that makes a strategy itself, right? That means you can define all sorts of kind of ways to kind of navigate your program representation and change it in various ways. And I think a lot of the stuff here is actually based straight away from Elko Visser's work, right, from the Stratego work. I think where we got significant further is that we aimed for implementing this and achieving the same performance as these TVM people were achieving, right? But they had built a very complicated compiler that had built in to know what loop tiling is and how to do this, right? And we said, like, our compiler doesn't know at all what loop tiling is. We just do a sequence of rewrites to achieve the same tiling optimization, okay? And we wanted the programmer, right, to themselves to define tiling as an abstraction in the scheduling language, right? So if a programmer thinks tiling is important, they should be able to express this as by themselves. They should have the power to express this as a concept that they can then pick up and use in their own setup. Okay, right. So we picked up with the case study, right? We did this matrix multiply optimizers for CPUs. We followed the same optimizations that TVM has kind of in their tutorial, how to change the schedule step by step, right? TVM gets a performance like benefit of like 200 times. This is logarithmic, I think, the scale, right? So that's a 200 times performance benefit you get by changing the schedule appropriately. And we try to do the same optimizations and try to express them as rewrites. And here's a bit of a flavor how that might look like. Okay, so on the left-hand side, we have the fundamental rewrites that are kind of important for us, right? So that is, let me see if I shift my cursor here. I don't think so. Anyhow, so this is essentially like when you can remove a transposition or add one. You can move a transposition past mapping twice over a data structure, right? You can, if you map over an array, you can also split the array into a two-dimensional thing. And then you apply the function to each element of this two-dimensional thing. And then you remove this additional layer we created, right? And this one, for example, it seems like a very silly thing because you seem to add a lot more work to it. But if you do this, then here you have more suddenly the choice for them to say, oh, let's do this parallel, let's do this sequential, right? So this opens up suddenly certain types of optimizations. You can fuse two maps together, right? And you can fuse a map and a reduce together in sequence, right? And this will all the rewrites, the basic rewrites being needed to do all of the optimizations that TVM was doing. So you can express something like tiling by composing these things together, okay? And this is what this strategy here describes, right? So this is a strategy taking a RISE, that is our functional language, right? A RISE representation in, and then this does certain things. It first applies a certain normal form, and then it will do kind of here this recursive thing, right? Where depending on how many dimensions we want to tile, we either just apply this S-split rule, which is the split join rule, okay? At a certain position, at the function of where we are applying this, or we have kind of a recursive definition, we essentially say like apply this to the next dimension, and then we have to reorder these things appropriately to achieve the proper effect of the tiling, okay? But it means we have a higher dimensional, arbitrary dimensional kind of tiling optimization, okay? Where the optimization, the TVM compiler is like, let's tile a 2D thing. If it's 3D, we can't do it, okay? And then once we have these strategies, right, built by the user, then you can combine them together in these recipes, right, where you say, okay, let's apply these tiling with certain tiling factors, so certain ways to split in our groups. And then we use this notation to say, this is the location describing kind of a traversal, how to navigate to a certain point in our program to say, let's do the tiling at the outermost nesting of two maps. Okay, but this is all here user-defined abstractions, right? So this is all stuff that is just names of functions and then recursively defined functions and functions that are essentially just look as simple rewrites. Okay. So that's how the flavor of our elevator worked back then, and kind of one set of kind of result slides. Okay, so the upper one shows that this really scales. So something like this thing you see here, which is 7 lines, right? This is the loop permutation strategy. And when you actually execute this and you trace and you count the number of successful rewrites you apply, and you apply here 40,000 rewrite steps. Roughly. Okay, so that means there's a sequence of 40,000 program transformations to take the original matrix multiply map like dot product, right, and turn this into a 6-dimensional tiled version, right? That if you then compile this and lower this to C, right, we achieve the same performance as the TVM compile. Okay. So that's kind of the main message. Okay, so we have competitive performance, and we can do really long rewrite sequences that you described in a fairly compact manner. Okay, with these things. Okay, and the hope obviously for us is, or was back then, right, to say like, oh great, like from now on, TVM and Halide, they've just waited for us. They're going to change the entire compiler design and they're going to adopt it, right? And they of course haven't done it. Cool. So that was kind of the success. This was a functional Perl, right? Nice application of functional programming, right? You get really nice compositional aspects, and you can achieve really good performance by doing these stuff, by describing these traditional compiler optimizations.
So whatever is how does it give direction? How do you know transformation. Maybe unfortunately yet another time.
All right. Okay. Right. So what we didn't try this in this experiment, right? So what you're asking is like, how do you know that this is kind of the best performance you can get or something like this, right? How do you know what are good optimizations?
I can imagine.
Of course. Yes. Yes. So what we tried in this work was really to say, we have already somebody else who has decided what optimizations to do. We're just trying to apply the same optimizations, right? So I mean, we avoided this sidestepping this interesting question of like, how do you know which optimizations are actually the interesting ones and how to pay off? Okay. We have some other type of work where we benefit from the compositionality, right? So where you start to actually explore a space of possible rewrites, right? But that's like, there are different ways how to think about this and how to do this. We have some preliminary work on this, where we can achieve also the same performance, but in an automated fashion, using a technique called equality saturation. That's a technique to apply rewrites in an automated way. Okay. That is looking at the same problem from a different perspective, exactly trying to answer this question of like, how we actually do this kind of. We are not interested actually in giving you a detailed description of what optimizations to do, but instead we're interested to finding just the fastest one, whatever schedule, whatever description might lead us there. Of course. Yeah. Of course, there might be multiple conditions, but often if you have not just one optimization aim, right, but multiple one, you often aim to have kind of a Pareto front. So where you then can kind of see like, okay, like I can trade off my two things, right, my two concerns. Code size might be one of them, energy consumption might be another, or whatever.
Yeah.
Sure. Yeah.
So you're not using Stratego yourself?
No. Well, I mean, there's a reason on implementation, of course, so that allowed us a very tight integration with our other compiler, right? So we just re-implemented this in Scala, which is where our entire compiler framework is built in. And I think we have at maybe very few points, we have made slightly different decisions than Stratego, but they are very tiny, okay? So I think conceptually, you could call the Elevate language just, this is like the design of these types, the combinators and so on, they are like 80-90%, this is exactly the type of Stratego. But it's in some sense applied for the specific domain and for our specific compiler.
And it's types.
Well, so our strategies are typed in the sense that they are polymorph over which program representation you are rewriting. So this RISE program is kind of the algebraic data type that represents our AST of RISE programs. Okay. But interesting that you asked that, because one of the follow-up projects we did, and we're currently doing with one of my students, Wang Xiao in Edinburgh, is that we are developing a type system for Elevate, in the sense that we want to statically know if compositions of rewrites are actually guaranteed to work, right? Or if they will fail because the second strategy can never succeed because the first one there will always be kind of a clash. Okay. Stratego is similarly typed to our stuff. They are they are typed in the sense that you know that you will get like a program back, but you don't know, or you fail at runtime, right? So you can think of this maybe as it's kind of dynamically typed, right? But with this work with Song, we're trying to move this actually to a static type system. Okay.
Yeah. So,
Yes. So we interesting. So the work with Hong Xiao we are doing, this is a fairly sophisticated thing. So he's using a structural type system based on row typing to express kind of how these pattern matching works. And then he has come up with an additional, what we call a trace system, to actually track all possible executions of strategies to start to compose them. And that allows us actually to have fairly complicated strategies and type them very accurately. So if you're interested, I'm more than happy to send like a draft of this. Yeah. Happy to get feedback on that work, actually. Cool. Any other questions on this? This closes kind of a little bit off actually the first part before we go into the practice part. Cool. James.
Quick question. So performance of the generated code is comparable, but what's the performance of the compilers relative?
Right. So you ask essentially, how long does this 50,000 rewrite steps take?
Yeah.
Okay. So this stuff in our Scala implementation takes a second and a half. It's really not a big deal. Okay, and this is like unoptimized, right? We actually have started to think about using Elevate to optimize Elevate programs, right? So that you start to see this itself as a data structure that you can then optimize and say, like, oh, let's fuse two rulers together or something. We in our current implementation, we just use this for debugging purposes. So you can inject you can have kind of a debug thing that you can then expect what does actually the rewrite looks like. Because we look, and that's one of the big downsides we actually see, is writing these not as straightforward as they here look like. As in like actually understanding how does this translated program, right, look at this spot? Yeah, not so super easy, right? What you do in practice is you inject a debug macro here, you get it like, oh, how does this look like now? And then you start to apply the next one, right? So it's a very fiddly process actually in practice. Cool. As I already said before, this was luckily selected to be presented at the communication of the ACM, and the ACM actually asked us if we want to make a funny video. And so my student Bastian, essentially, what he took is said, hey, let's do a cool video. Let's do a Hollywood-style trailer. I'm like, cool, I'm on board. And then he said, let's write a script. And then he took our abstract, posted it to ChatGPT, and said, like, generate me a Hollywood-style trailer of two scientists advertise their work. And then we edited this, and that's what came out of this.
Where technology is advancing at lightning speed, one team of brilliant researchers dared to push the boundaries of what's possible. They set out on a quest to create something that would change the way we think about optimizing programs forever. And they succeeded, introducing Elevate, the functional way to achieve high performance. To this day, the predominantly used imperative languages force the programmer to intertwine the code describing functionality and optimizations. This results in a portability nightmare.
But I had a vision. Functional language for describing optimization. The key idea is to separate computation from optimizations. We then build a strategy language with the same standards that typically only apply to languages for computation.
With Elevate, anyone can define their own optimization strategies without being restricted to a set of built-in optimizations. In Elevate, program transformations are rewrite rules. Complex optimizations are expressed as compositions of simple building blocks.
With Elevate, programmers describe complex compiler optimizations, such as tiling and vectorization, simply as sequences of rewrites. The paper shows that we achieve competitive performance to the state-of-the-art domain-specific compilers TVM and Glide, which require complicated implementations to perform the same optimizations.
Elevate is a game changer in the world of program optimizations. Its ability to specify composable optimization strategies makes it stand out from the rest. There has never been such level of flexibility and control in any other programming language. It's been published as a functional kernel at the prestigious ICFP 2020 and selected as a research highlight of SIGPLAN and the communications of the ACM. It is now official. Elevate is the future of optimizing programs, but don't just take our word for it. Listen to what experts in the field have to say about it.
Elevate is an optimization language that supports abstraction and reuse properly for the first time. As a result, we can enjoy elegance and state-of-the-art performance, both at the same time. Sometimes we can have our cake and eat it too.
Don't miss out on this game-changing technology. Elevate, the ultimate programming language that will elevate your code to new heights.
Okay, so this is what you get when a PhD student has too much time and ChatGPT helps you to add the confidence that neither of us would have in the first place. Anyway, good fun. Cool. So the second part of the talk, I'm now going to talk about the practice aspect a little bit. So this now goes to, okay, these ideas they seem compelling and nice, right? And we have some evidence or some hope that the performance we get actually is good, that we have nice properties and so on, right? But how do we actually convince compiler engineers to actually pick up some of these ideas, okay? And for this, I'm going to talk a little bit about a compiler framework that is currently essentially popular used in the compiler community, who would have never read any of the ICP papers on Ecovisa, or possibly ours. Okay. And that framework is called MLIR. Okay, MLIR is a framework implemented in C++, comes from the LLVM community. That LLVM, I guess, is like a name that most people in kind of the language universe at least have heard of. And MLIR is kind of a fairly novel framework that has been introduced like 3-4 years ago by colleagues at Google back then. And the idea was to facilitate sharing of compiler infrastructure, particularly of compiler intermediate representations and optimizations over them. Okay, so the idea is different to LLVM-IR, which has one intermediate representation to represent C-like languages. Here, you can define your own, what I call dialects, which essentially is a set of common abstractions, okay, that might model a specific domain or a specific set of features, okay. And then the idea is that you start with a maybe high-level representation, let's say with a TensorFlow graph. You have a dialect that captures the abstractions of TensorFlow directly. You might do certain type of optimizations at that level. So you might think about thinking at kind of the TensorFlow graph and doing kind of merging of operations at that level. Then you might turn this into kind of other dialects, such as there's, for example, a dialect is called affine, and that has a lot of compiler theory on polyhedral optimizations, which is a theory of thinking about transforming loop nests in different ways. And they use polyhedral analysis, which sees this as kind of a geometric structures, and you start to kind of move stuff around, be careful that each iteration will not override something from somebody else. Then you might turn this into a low-level dialect, which might capture certain abstractions for a hardware architecture, right? Such as how a GPU works, okay? And instead of having one intermediate representation where you lose out at the top because you have forgotten what was a TensorFlow node, right? Or you have an IR that is not specific enough to allow you to talk precisely about how hardware works. Okay, that's the hope, that's the promise. So how does this kind of how-levelly look like? Okay, so you might have something like this there, where you say I have a convolution, 2D convolution layer, right, or operation that has certain high-level types, right? So it takes tensors in, cool. You might then translate this into a certain loop nest. And then that might be translated into, for example, an execution on the GPU. Okay, and something like, oh, I'm launching a kernel on a GPU, right? Or I have a loop that has certain properties, and therefore I can transform it. But this is then baked into these intermediate representations that you have there. Okay, so I'm focusing mainly here because we now talk about doing compiler transformations, right? So we're going to think about how to transform these representations, okay? And they don't look so nice function anymore like the stuff we saw before, right? The MapReduce stuff where I showed you the nice rewrite patterns, and I'm like, oh, that goes to single net, right? We would like to be able to say stuff like this on this representation as well, okay? So that's where the practical aspects come in. Okay, so this is an example of how you can express matrix multiplication in this MLIR framework, okay? So you can see here there's a triple for loop nest. Okay, and then in the innermost one, this here is going to do a dot product, right? We are loading things from memory at certain locations. We're performing a multiplication and then additional addition, and then we store the result back. Okay, so you might have kind of a rough idea. Okay, this looks like roughly like matrix multiply. Okay. Let me highlight a couple of features of this representation. Okay, so in MLIR, you have these things here, we call them operations, okay? They represent some computation. In LLVM-IR, they're called instructions, but here they kind of take a little bit of a bigger term because the semantics of what this F94 actually does or how it executes, right? That is up to whoever defined this operation, okay? Then we have operations can carry attributes. This might be static information, like such, for example, here, a certain loop bound, right? So that might be a static information you carry, or you might have any other kind of information that is static and not dynamic that can you represent by just attaching additional metadata to it, okay? there's some level of a very simple type system, right? But we have essentially just basic types, and there's a function type, and that's pretty much it. Okay, but you can express something like a tensor type, for example. They can also be kind of manually defined, and they can carry some form of additional kind of metadata. For example, this here is a two-dimensional dynamically typed thing. Okay, they would really benefit from dependent typing, by the way, but it's a different story for them. Okay, and then they have, and that's kind of partly new, at least part of it, they have a thing that an operation can have what they call a region, which is these curly braces, right, which allow us to nest stuff. And then inside of these regions, right, these things, they are called blocks. We're going to allow them, and the block is always going to be executed from top to bottom, okay? And it's essentially a list of operations, right, which you just essentially execute from top to bottom, okay? In particular, these regions who allow the nesting of stuff, they are a thing. This is new in MLIR. This didn't exist in the LLVM framework that existed before. Okay, so they would have not been able to represent a for loop in this way. In LLVM, you would represent a for loop as a sequence of branches and checks. So you would compile this down, would say, oh, there's a check, and then I have maybe my body, which would be a block. Right, and you would have a test at the beginning that says, oh, if my condition is true, I jump over this block, I stay here. So it's a much lower level representation, right? And here we can now represent something like this. Questions? We come to this. So the control flow inside of a block, at least if we talk about SSA, which is what I'm only talking about, okay? Then inside of a block, it's always sequential from top to bottom. Okay.
Can you jump forward?
Yes, you can jump. You can jump between blocks. Okay, so this is here one block. This could have a label. You could have another block below here, and you can jump across blocks. And the blocks in one region actually they form a control flow graph. So meaning they can jump to one or another, right? And at the end of a block, you will always need kind of a terminator that says where to continue. Like, should I return? Should I jump to somewhere else? You cannot jump straight into a block to instruct. You can only jump to the label of a block. Okay. Okay. And then interesting, like as a consequence of all of this, right, these regions, they introduce scopes. Okay, so when I say here this percentage I, okay, this is only visible or defined inside of these curly brackets, inside of that region. That seems a very natural thing for us as programming language people. Okay. And then inside of the block and also actually across blocks, the main thing that we care about in this representation is an aspect that is called dominance. Okay, dominance comes from graph theory. And the idea there is that a value must be dominated, a using of a value must be dominated by the definition. That means every possible control flow through your program, okay, you must have passed the definition before you come to the use, right? So if you have one possible way to kind of get to a point where you have executed and you have not seen the definition, then there's no dominance, and then you can't use this value statically. I will show an example of this in a minute. But here's a very simple example, right, where the percentage A must be defined before it's used here. Okay, so if I swap these two instructions, then this makes not much sense. Okay, that's a very intuitive thing. But this dominance becomes a little bit more interesting and tricky when multiple blocks are involved. Okay, we'll show an example in a second. Okay, but you can think, because this dominance is all we really care about, I know it's the main thing we care about, you can think about this also as kind of a graph-based representation, right, that we have just a textual representation for. And this, what we call in the compiling community, def-use chains, so meaning I have here my use, my definition. These are the chains we really care about, right? That means the API to navigate this, you can ask like, where's my use, right? Where are my where is my def and where are my uses? And you get a setback and so on, right? And this is how you can navigate this aspect in there. Yes, and then one other important thing, this thing is called SSA, single static assignment. That means this percentage A right? You can only one time assign. You can never kind of change the definition of percentage A. So this percentage A will always represent this law, right? In that sense, it's kind of single step, right? Okay, let's understand the single static SSA a little bit better. Okay, so this is now a slightly different notation, okay, but here's an arbitrary sequential program, right, which does the while loop and some assignments for values, okay? And you can turn this into a control flow graph, okay, where you now see these are these blocks that I talked about kind of before, okay? You can think of them at least like this. So meaning we have some instructions that we do before we enter the loop. And then you would compile this loop away by saying, okay, there's my control flow. I have now the condition. If this is true, then I go here. If this is false, then I return, right? This is this while here. That means this thing here is my loop body. And then here I have another if then else, right, where I go in here, okay? And when we now talk about dominance, then, for example, I can say that it's okay to use K here, because every possible control flow that can lead me here, okay, K must have been defined before. This is this K. And that's the dominance relationship between these two, okay? That's a bit fiddly for, like, because you think about these graph stuff, right? But this is literally, this is how we think about this in the compiler community. Right, this middle bit, right, is not yet in SSA form because you can clearly see that I'm reassigning J twice, right? So the same J can either mean 1 or it can mean K. So to turn this into SSA form, we version these numbers, like these things, right? So we say this is J1, this now becomes J5. So when I say J5, I always mean this. When I say J1, I always mean this, okay? You still have all this dominant stuff in here, okay? But you now have like one interesting new thing that's also slightly unusual, which are these weird phi notational things, okay? They're a little bit of a weird thing. So what are these phi? They're called phi nodes. And these are kind of artificial things, or artificial constructs, right, that have been added by the inventors of SSA form to help us to distinguish, right? When I come here and I want to talk about J, this could either be the J from here, or it could be the J that comes from down here when I've already gone through the loop. Okay, so this phi node, which like the legend after this was called the funny node, okay, this essentially selects either left or the right-hand side based on which control flow I entered when I came into this block. So what is the predecessor of my control flow class? Okay. Seems also a little bit of an odd design maybe, but yeah, this is SSA. Okay, this is the structure that LLVM works with. This is literally the representation. Okay, and that means we have here kind of, you can think of this a little bit as kind of merging the data flow, right? So depending on where this comes from, right, we decide then on the version. Cool, and that's pretty much kind of SSA. So dominance is important when you have those really funny fields, okay? But in, this is literally what SSA means in the LLVM community, in the LLVM universe. But for MLIR, sorry, you have a question, ask me a question.
How does that relate to the whole dominance? If you're using J4 in the phi, you know, when you just start, J4 has not been installed.
Yes, that's true.
Dominance is a bit different for the phi nodes.
Yes, so the arguments of the phi nodes, you're absolutely right? So clearly here there is a control flow path for the phi node, right, where J4 is not in scope, right? But because the phi node is kind of funny, right? It is clearly what's kind of the only requirement you really have is right that one of these edges kind of must be, right? Okay. And then it can always select, okay? That's an absolute correct observation. What still is important, right, is that this J here, right, that is still dominating these all these instructions where you see the J, right? Yeah, good point. Okay. And now we are kind of, after I explained to you what these phi nodes are, and they are special and they're a bit weird, right? Now I'm going to tell you that MLIR threw them out. Okay. So what did MLIR do? Okay, so MLIR threw them out. So here's an LLVM-IR thing where I do have a phi node. Okay, let's maybe understand this example first before we go to the side. This is this thing. Okay, so I have 4 basic blocks. I call them here A, B, C, D. Okay, and then I have here like my x1 is 5, x3 is, sorry, this should be x2, I guess. Oh, sorry, no, this is, I'm not sure. This is 3, or this is a constant 3. This is x3, this thing. So that's x minus 3. Okay, then I have condition, and then I branch based on the condition either to B or to C. Right, either left side or right side. I branch to the left side. Okay, then I have here my constant, do I multiply, do a copy, right, and then I branch to D, or I go to the right hand side of my instruction branch together as well. And now here I have my phi node, which merges my control flow together. Okay, so meaning either I meant y1 or then y2, depending on this thing. Okay. One other observation maybe to point out is, right, dominance, we talked about this before. This x2 here, right, that is defined all the way up here. And that's fine, because I always have to exclude A before I'm going to D. But this W1, for example, I could not use here because this is only defined on one side of the branches. I could not use this down. So this would be ill-formed if I would use W1. Okay, fiddly. Okay. I got come with a better intuition in the future a little bit, but this is a representation that compiler people think about, right? MLIR, okay, so not LLVM-IR, no phi node, okay? Hooray, what have they done instead? Okay, so they introduce regions, we talked already this before, they introduce a scope, okay? But now these blocks, which we talked already before, they can have parameters, like functions, okay? But they don't introduce the scope. Okay, they're just labels you can jump to and they have a parameter. Okay, but if they, in some sense, if they would define the scope, right, then this x2 here, right, would be defined in the scope of A, but you can totally still access this fine here because of this dominance thing. Okay, that's why I'm highlighting they're not defining a scope, a local scope. Everything that you define locally is only visibly local. It's still visible kind of across, at least some of it. We'll come back to that in a minute.
Right, and now you have dominance with respect to your block parameters.
Right, and then you have, I mean, the dominance still exists exactly like it did before, okay? But you just remove the phi nodes of merging this thing, right? And instead, when you branch to this block which has a parameter, you now pass the value as an argument along. So this is like a function call. Okay, where you say go to D, and then when D, you have the parameter there, right? Should actually be this one, right? So in some sense, what we talked about when we talked about phi nodes was left hand side, right hand side, which one should it be, right? And you say, okay, this one, right? This is the parameter of D, and this is the argument of that call side or that call side. But that argument has been kind of pushed inside on the wrong side, right? It's kind of a weird, I mean, if you think about it this way, it's a bit weird, right? But if you see it here, it makes much more sense, right? Here's the function call, or the branch call, and then here you have the parameter and the branch, right? And that means you don't have to think about these phi nodes anymore, they're gone. You still have this dominance thing though, okay? Okay, this was kind of now the precursor for like a very weird representation. Right? And that took us a long way away from these nice, funny video that I showed at the beginning, and everything was nice and was functional and so on, right? Reminder, right? We want to somehow perform composable rewrites on this, okay? In particular, we want to, I call this here sane. We want to kind of avoid certain things, right, that might go wrong, okay? And I will actually highlight more the stuff that might go wrong, and then I will show a little bit of stuff of like how we currently think about maybe mitigating this. And then I will also talk how that relates back to the functional side. Okay. So if we think of doing now rewrites over this representation on the right-hand side, okay, let's start with something super simple. Okay, just establish some base things that we have to think about when we do rewrites, right? I want to rewrite x plus 2 to x shift to 1, right? So if I don't have additions, I don't want to do +2 or whatever, then I do shift. I think actually that should be multiply, not a plus for this to be semantic correct, but let's ignore this, right? It's just a transformation, okay? Right, so in MLIR, this here, I would represent this way, okay? Meaning I have here the free variable percentage X that is defined somewhere, I don't care, right? But then I can't write the value 2 straight away in here because the single static assignment form, every single line has to be name, one thing, and then arguments possibly, right? And this here is one of these attributes that says, oh, this actually should be constant of value 2, okay? So in the functional world, this would be kind of like you have a let binding and then you immediately say after you've let bound this, afterwards you should bind this, okay? So if I now want to rewrite this into this one, where I'm saying like, great, change my constant, okay, and then change this, multiply just the argument of this, oh, sorry, this should be a shift actually, oh, it's all wrong here. Okay, but you get the point, right? So one important point to highlight here is, I think now I actually change it to the correct version, right? Is that this output gets the name again, right? This result thing, which that doesn't exist here. This is kind of just this like, oh, it's used somewhere in context, okay? We don't know where this result will be used or how many times or in other blocks or wherever, right? So if we want to think about a rewrite, we want to kind of just say like, oh, replace this with this, right? On the right-hand side, we should ideally, at least semantically, right, not change this result thing, because then I have to suddenly think about where is this thing used in which context and so on. So, right, we think about this by saying like, okay, let's change the right-hand side of this assignment, okay, to the new operation at the root. And anything that depends on it, let's just stick it on top of this, okay? So that's kind of one way to think about this, right? But let's see, highlight like, we don't know where this result will be used later, so we can't just remove this or deal with this, okay? And then one other important thing, this tool here, right? This now has a let bound name in some sense, right? So this has like an SSA name. So this could be used anywhere else later as well. We can't just remove this because it could be that the next line says, oh, I want the same constant 2 value reference, okay? So meaning we can only remove this if we are sure that it has no users, right? Or we just keep it, and then maybe we do kind of that code elimination later or something like this, okay? But it means even something as simple as, oh, let's change the SSA, sorry, the AST from this small things already requires a little bit fiddly because this is not how these programs look like. Everything has a name, right? And that means you always have to reason about how long these scopes of these names are. And so on. Okay, so that's one massive problem one thing to think about. Okay, our practical solution at the moment is we keep this, we do literally this, right? So we keep this name and we keep this, and then later we do one kind of that code elimination over this entire thing, kind of garbage collection or whatever you might think of this. Okay. And then I talked about sane rewrites that we want to do, right? So what could possibly go wrong when we do rewrites over this representation, right? Here are 3 versions of what could go wrong, right? So you could swap these 2 lines, and by doing this, you break dominance, right? So you could just decide and swap kind of 2 names around or 2 lines around, right? Or in whatever rewrite you do, you could end up with that you have actually a use before you have the definition, okay? You could make the same thing actually also across blocks, or even worse here across regions, right? So for example, here, we now refer to this percentage A that actually is defined in this other region, right? So that means there's some scoping still going on we have to think about, right? These things, scopes, right? And one other very easy practical thing is like, these regions have to end with a terminator. So I have to have like a last statement. Like for example, this here is like a if then else, which gives kind of you a value back. And they then have this yield, right? Which says like, oh, should I give the value from the left-hand side or the right-hand side, right? You could just try to remove these. And then suddenly this is kind of inconsistent in the sense that this shouldn't type anymore, right? But it also maybe at a more fundamental level, it breaks this invariant that each block should be finished by a terminator. Okay, so these are problems we have to think about when we want to define rewrites over this universe. Okay. So my student Martin, which I think is a picture of a very small at the bottom left, right? He's now starting to think in terms of these SSA to try to fix kind of, or try to come up with analysis that address these individual concerns, right? So that might mean we have here this thing where we remove a terminator, right? Currently, if you write a rewrite that does this, you can apply this at runtime, okay? And then after you've applied it, you can run kind of a dynamic checker over this thing, and then it says like, oh, something is wrong. And what we want to do is we want to essentially do a static run over the rewrites. We want to just look at the rewrite and say, does this rewrite break or remove terminators? Okay. So Martin is now coming up with these type of like local like analysis to look at the rewrites and look into these are these are terminators that we have matched that we might be removing. Are we adding new rewrites? Sorry, are we adding new terminators? Will they replace them and so on? So it's a super tedious process, right? But that's kind of the consequence of thinking in this SSA terms. Because now you have terminator, you have to think about dominance, right? So there will be another analysis to look at dominance and so on and so forth, right? And in some sense, this is kind of the practical way to collaborate also with colleagues in that field, because that's the terminology they understand and the problems they understand, okay? But here comes kind of the twist, okay? Here comes the twist, like, can we maybe go back to the functional world, right? And say like, lambda calculus to the rescue, maybe we can think about this and these type of problems, but we think about them not in SSA terms, right? But we think about them in functional terms, okay? And that part is a bit loose because we are kind of, I'm highlighting a bit of the correspondence that we are aware of. And some of the correspondence that kind of fall out of this, but I think I'm still interested and I'm still figuring out what that actually means for these checking of some of these aspects that we have, that I've highlighted. Okay, so this is a early 90s paper, okay, from Andrew Apple, and he actually points to another colleague called Richard Kelsey, who have in the early 90s pointed out that SSA, this form that we saw, right, where we have dominance and we have this finals maybe, or we have now these block arguments, right? That actually you can think of them as functional programs. Okay, I'm going to explain kind of that correspondence here. So look on the left-hand side here. This is the SSA form that we talked about before. It has again these finals, but you can think of them the same way as we had before. It's like when you call, you can pass an argument from. Okay, and Andrew Adams gives this functional program, okay, as an equivalent representation of this. Okay, and there are some correspondences here. Okay, how should we think about this? Okay, so we see the first block here. This is literally the first line, right? So I let bind my 3 I1, I1, J1, K1 values. And then I have a block here. And for the block, I define a function, F2. This function takes two arguments, right? Or has two parameters, K2, K2, right? This is exactly the same observation we did before with these block arguments to say, oh, these actually should become arguments to the block. And when you kind of resolve these finals, you should, when you call them, actually pass a proper value, right? That makes now kind of this correspondence maybe even more obvious, right? So F2 represents this block, and these two finals, they become the parameters of these things, okay? And then later, when I do control flow, okay, then I call these. This is the first call, right? And the second call that comes here, okay? And then either I pass J1, K1 along or J4, K4, okay? Right, and that's kind of the general idea. Blocks are actually functions, okay? And control flow, right, that are represented here with the edges, and then the finals, right, they actually become function calls. Which could mean you could replicate in some sense this graph by analyzing here the function calls among these functions, okay? So that kind of gives us an intuition for the one side of it, okay? This is not dominant, well, I mean, this is, the finals and the block arguments, okay? But what about dominance, okay? So we have here, as I pointed out before, like for example, this dominance of this part here, right, in this block, that is actually dominated by K2, right? I mean, definitely we'll always go here. That's why it's fine to use this in here without explicitly passing this along these edges, right? There's no final where I pass these values along. There's no function. Okay. Well, how does that fit with the picture? Well, then that pretty much fits into the picture by essentially saying like dominance becomes scoping, right? So meaning everything that's nested inside of function F2, right? That's all dominated by F2, right? Because that means now here, like I have here my J5K thing, so I'm not sure where I'm referring to K2 again here, right? But then I refer to this again also here and here, right? And I'm allowed to do this on the right-hand side because they are just in scope, okay? On the left-hand side, there's no scope for this. I'm allowed to do this because they are dominated, okay? So that's the kind of fundamental intuition that is behind, right? And so possibly, right, thinking functionally, can I actually avoid breaking dominance across regions and stuff by ensure proper scoping of the functional representation of my rewrites? And for the terminators, for example, right, can I just check that my programs are actually, that my rewrites are well typed, right? So that they leave me in a well typed state. And maybe I don't care actually because it's obviously stronger, because it gives me kind of a guarantee that maybe my rewrites are typing preserving. Okay. Maybe I care actually for slightly less. Okay. But these are kind of the checks that I might actually be interested to formulate. Okay. So that's kind of where that part ends for me at the moment. Okay. So meaning these are intuitions that I have, and we are thinking about adjusting this and like applying this. But it still leaves to a certain extent a gap, because the question is, should people who want to express these rewrites in this language, right? There is no scoping here, right? In some sense. I mean, this is fairly straightforward to see that this is broken in all sorts of settings. And maybe there's some scoping here, right? But for certain rewrites, they think about dominance. They don't think about these scoping things, right? So how do we bridge kind of the gap from somebody who thinks in terms about, oh, this breaks your dominance, but actually we might perform the check on a functional representation where we want to check where its scope is. And this type of correspondences are not fully clear to me in my head yet. Okay, so that's kind of a bit work in progress stuff. And then I have like 3 more slides at the end now to kind of come back to, once we have solved kind of how to express single rewrites in the setup, right? It is fairly obvious to us how we can compose them back together again, because that's actually what this elevate stuff I talked about before explains, right? We can preserve the same typing ideas. We can apply the same compositional ideas, and that will allow us to express optimizations such as, let's take a loop, split it in 2, and then unroll the second one. And we will be able to express these type of compositions. These are examples that actually compiler colleagues from us, they say they can't express currently, but they would like to express. Okay, such easy things like this already. And this might look for us something like, we say, first split the loop, then go top to bottom, skip the first for loop you find, and then unroll apply the second unroll or something like this, right? And this again might look reasonable, right? But we have to then these individual rewrites, right? As long as they satisfy these type I've given at the beginning, right? So either they rewrite, succeed and give you back a rewritten version, or they fail. And this stuff actually is a fairly straightforward idea to pull over from the elaborate work before. And for that, we actually have already a small prototype working, which works on an immutable version of the IR, because the rewrites that MLIR currently does, they're all mutable, meaning you can't do backtracking when something fails, right? But that's quite essential for our strategies, how they work. You think of something like these top-down traversals, right? They will start to apply, it might fail, and then they have to go back. So we need kind of this immutable version. But we've implemented a version around this, and we actually see that in practice, it's much slower than doing this destructively, right? So than just doing it kind of on a mutable version, but it's still much better, the version we've implemented, than if you would kind of do a full clone of every single rewrite, right? So you copy the entire IR over time. which is kind of the worst kind of. And yeah, this is a kind of some kind of final kind of results. I thought ending with something that actually works. And that's me finishing with essentially kind of the two projects, kind of the Elevate stuff I talked about before. And then on the MLIR side, we do all of our work now in a Python version of that framework that we developed with colleagues from Tobias Kosser's group in Edinburgh that allows us to prototype some of these ideas on these MLIR representation much more quickly than going into the C++ world, which is what we did before. Cool. And with that, I'm closing. I'm happy to take more questions.
Fantastic, thank you. We had quite a lot in the running.
Which was good. Yeah,
it's good. Can you express dominance as some kind of type system on blocks? So not just that they have an input scope, but they also have an exported scope. And
so then you kind of say
dominance is kind of reachability in.
Well, generally, when you are in that structure, right, then the dominance computation is usually, that's fairly easy in some sense. At least that's what these are optimized for, right? Essentially, because, and that's kind of the point, right? All of these things, they're kind of, that's the graph nature, right? They are all connected via these step use chains. So the entire always keeps track where it's been defined, where it's been used, right? And you then might have to only check in some sense, like, or is actually the thing like used before it's defined? There's probably the question, what does before mean here, control flow terms, right? The bigger question for us is, right, when we express these rewrites, which already is kind of a bit of a question, how do we write these rewrites in the first place, right? Currently, there's a very imperative nature how people write these rewrites. So something like this tiny rewrite I had here, right? They would write this as there's some pattern described to match this. Then on the right-hand side of the rule, they would say, replace this with this, and replace all users with this, and delete this operation stuff, right? So there's very imperative, destructive nature to think about this. Some of these operations, like removing something, right, is only valid if there are no users of this, right? Otherwise, you can't do it. But how do you statically check that there can't possibly be a use of it, right? So ideally, we would have kind of a more declarative description of these kind of a before after, where people don't write actually kind of an and then remove this and then add this here. And then we would like to check these properties, right? So particularly the property that the right-hand side we are generating, that this will be well dominated, as like every block has a terminator and so on and so forth, right? And one thing we could think about is we could think about taking this program, turn it into a functional program, apply the rewrite there, check that it's well scoped, that it's well typed. That the rewrites are, not that the programs are, right? That the rewrites preserve these properties and then go back, right? So that might be one way to think this. But then there is a little bit of a gap of like, okay, how do you actually make this nice for users?
Yeah.
And so on and so forth, right? But like scientifically, this still might be interesting, okay? And I think this is also one way to think possibly about semantics for MLIR and other stuff, right? So that you could see kind of this close correspondence of a way to understand how to execute or think about these programs, right? So you could take an arbitrary MLIR program, turn it at least syntactically into this, and then the question is still, of course, like what are these individual operations that you do, right? Yeah, I think James already saw that I have here my PyCharm open. Actually, see if I can pull this over, right? But this is like one version of this, right? So you have here on the left-hand side, MLIR. You have like block, and blocks, and that all nested in the region. And that's a Python program that represents the same stuff, right? Where, of course, now I don't know here what, I've now turned here something like arrays.li just in the plus, right? But you could leave this kind of almost uninterpreted and say there's a function called aris at I that has certain types, and then you at least have a representation of the same thing, right? And here now, here you see exactly the same again, like each block turns into a local function that's nested. And then by how they are nested, for example, that B4 is nested in B3, that actually indicates that this entire block is dominated by this. Okay. So that's like one fairly, like, I mean, clear way, if you like, how you can connect these two units together.
So the MLIR is different dialects, and you rewrite within the dialect.
Not necessarily.
Okay. So basically lowering to a different dialect is also an optimization.
You could see that as a rewrite. It's not necessarily that doesn't have to be the case, right? But you could have a rewrite that, for example, specifies or turn this TensorFlow node into this sequence of for loops and I don't know what, right? You don't have to see it that way, right? You can always make a full pass over the entire program and say like, oh, I need some context, I need to make decisions, and I need to, right? But you could possibly think about expressing lowering passes or optimization passes. Sometimes it might be difficult to express an optimization at a certain abstraction level, right? So for example, in TensorFlow, there's no memory or there's no idea of memory, right? So to say like, oh, I store this in memory, you might not be able to say. So it might be that to express this, you might kind of combine changing at the same level and going one level down. But I think ideally we want to avoid doing this because then it gets these optimizations get suddenly very tightly integrated and complicated to understand. But technically for me, these are all just rewrites, right? I don't care. Like, I mean, for me, the difference between a dialect or not is literally just the prefix for the things, right? And what dialects are.
So MLIR allows you to mix and match.
Yeah. As long, I mean, ideally you preserve typing, but I mean, also you can just check for 5 minutes and then as long as you've restored your typing, then it's fine, right? So you have much more loose control over this because like there are types, but you can also ignore them to a certain extent. I mean, of course, at the end, when you want to actually generate executables, then you better generate something that actually is like well typed at that level. Yeah, I mean, there is still the full LLVM IR and the entire implementation sets completely, but yes, exactly. So there is one dialect that is the LLVM IR in MLIR. So meaning you can go kind of this flow down, and you can at the end up with a program that is in MLIR, but is only using LLVM the dialect, and then you can kind of also shove this over the horizon and use other tools. Yeah. If anyone is actually interested in this type of stuff, there actually will be in May, 10th of May, I think, the Euro LLVM Developer Conference will be happening in Glasgow. This is like a fairly industrial event, but I mean, people come from all over and they discuss LLVM. And we will organize in Edinburgh the days before that an MLIR workshop that will be more specific on the MLIR side. Yeah, I'm happy to send like some follow-up information around that if people are interested. The LLVM developer meeting costs money. Our academic event won't.
Oh, question in the chat.
Oh, question in the chat. But yeah, Hans Wolfgang, maybe you ask your question first.
First of all, yeah, iterate brings us close to the whole grade of high-level efficient currency.
Yeah.
That's really cool. The question or rather observation first on the architecture front. There's quite a lot of development in terms of architectures coming out supposedly to support the machine learning or similar.
Yeah.
So the question is, have you looked into one of these architectures as items? Because there would be a good thing to leverage.
Right. I just repeat the question. I'm not sure how much actually. I mean, now I'm realizing we also have remote people. But yeah, so Hans Wolfgang is asking how much we have looked into leveraging kind of AI accelerators and hardware, specialized hardware as a target. And we have only looked into this in kind of limited settings, but we have. So we have done, for example, some work where we extended our code generator and our rewrite techniques to cover a hardware extension that is specific to NVIDIA hardware or tensor cores. They can do kind of very small matrix multiplications very efficiently. And these are kind of fairly simple additions for us, right? So to just say like, oh, there's a new, we think of this often as like there's a new API to cover, right? So there's a new low-level interface to go for. And then you start from that low level, try to capture what these low-level API actually expresses. You try to turn this into functional patterns and give them types. And then that means we can express kind of them computationally. And then you need rewrites that actually explain how your other language constructs kind of target and go to that, right? So target this. And that sometimes might lead to very specific rewrites, right? So we had like for this, a rewrite that literally just looks for matrix multipliers that are 4x4 and with a certain data type. And then you can either use these elevate stuff I talked about to kind of manually decide, or do this stuff and then apply this kind of use special hardware rewrite, okay? And then some of the other research we have done, which is also what Rob actually is asking remote, where you apply more stochastical search techniques, machine learning techniques. I talked about this equality situation, right? You can kind of also think about these and kind of you throw more rewrites into the mix and then you hope for the best, right? And I think there's much more work to be done in this to also explore how do we come up with good kind of functional hardware descriptions, right? So how do we capture the behavior of the hardware in meaningful units to facilitate this type of kind of rewrite-based optimizations?
I think the interesting.
Yeah, plenty of challenges. I think just mention one challenge because I think there are plenty, right? But one challenge we see with our lift-rise functional representation is that we don't really, at this functional level where we say map reduce, we don't really have a way to talk about memory particularly well. And that means to indicate stuff like, oh, let's put this in this memory region, and then let's do some padding around here, and let's do some, I don't know what, right? Really low-level details. We really lack a little bit of kind of vocabulary and also of capability to talk about memory, right? And that's just a natural thing, I think, at that abstraction level, right? And we have done with Bob Atke at Stress Clyde some time ago, like a language that adds kind of imperative features to our language. We use this currently in our compilation flow. So we go from purely functional to an imperative language. And you could also think of doing rewrites then at that imperative level, right? I mean, not a full-blown C, everything can be aliasing, I don't know what, but you have a very minimal imperative language where you still understand that rewrites are, which rewrites are fine to apply, right? You might also have, like, I don't know, effect systems, all sorts of other stuff to keep you in order, right? To then do rewriting at an abstraction level where suddenly you can very naturally talk about memory and other stuff. So I think there's kind of also a natural abstraction gap that we have to acknowledge and should not kind of say like, oh, functional is everything you ever need, right? At some point, we do actually go down. Cool, and then I just read out the question that Rob is asking, saying about the first of my talk, the ICFP 2015 paper, so that explains the kind of computational language lift-rise that we talked about, that was briefly to be seen. That comes, that is this MapReduce style of extreme computation. And in that paper in 2015, we used some fairly simple kind of stochastical automatically search for the best rewrites versions, right? And that worked well for very small programs. And then when the programs become larger, then these simple techniques we used then, they don't work anymore. And that means either you need, and that's something that we haven't really done, right? You need reinforcement learning or some of these new super sophisticated large language models, generative models, I don't know what, right? And then there's the question, where does our training data come for to feed them and so on, right? So either we need significantly more sophisticated machine learning techniques to scale better, scale further. That's at least my impression, right? Or we do non-machine learning, but still automated techniques. And these equality saturation technique that I mentioned, that is a technique to apply, to explore a lot of rewrites very aggressively and quickly, but it doesn't use machine learning. It's just a very clever data structure. I think sometimes we forget that we can also do good computer science and do interesting stuff and solve problems. And we don't need to just say like, oh, it's so complicated, let's give up and learn. right? And let's solve everything by scale. So I think there are other ways to be explored that can still be automated, right? Or help with automation. And the question Rob is actually asking is like, are the humans better or are the machines better, right? And at the moment, I think in a lot of the stuff we do, the humans are much better, right? So we don't yet have a technique based on what we have shown where we just say, press a magical button and we generate code that is like 20%, 50% faster than the stuff the TVM people have written, right? At the moment, that's not the case. But that doesn't mean that it can't be the case, right? But I think where I actually find the most interesting stuff is when we combine human expertise to maybe guide and drive an automated technique. So meaning we have intuitions, right? Let's try vectorization, let's try tiling, let's try whatever, right? But currently we are either always to be forced to express everything at super detail. So you write your C program at the beginning with like all indexing has to be correct and everything has to be perfect, right? And or we kind of say like, oh, it's fully automated and machine learning will solve all the problems, right? And I think there's a huge space in the middle where maybe this intuition of like, I quickly say, why don't we try out 5 different tiling schemes? I want to be able to say that to the machine. And then that cuts my search space down massively. And I want to automate kind of that process. And if that is automated like equality situation or machine learning or like type-driven synthesis or whatever techniques we might use there, then I think is a huge space where like human drive, right? And the machine catches up. A bit like maybe how you think about automatic interactive theorem proving or like other fields where maybe you kind of set certain goals and you try to automate a lot of the tedious stuff. So I think that's aspects we see, right? And for this paper, like the 2020 paper, like Bastian, my student, was very good because he designed the language and then he used it, right? The next PhD student that came along, Thomas, he used the same language and then he got so frustrated that it was so tedious and he had to pay attention to all the syntactic variations in his programs that he then went away and started to look into this equality situation to make his life easy, right? So if like that's a sign where like the first student says like great idea, the second student says like I buy into it, but I invent something better. So I think there's like much better stuff to be still kind of invented on that side. So Rob says, things stochastical search is slow for optimal compiling larger functional programs to emit lots of CO2 when trying to meet the original aim at reducing CO2. Yeah, that might be a good point of like, if we actually need longer to optimize our programs than they actually eventually run for, then that might be a bad thing. Yeah, I think it's not just slow, I think it's a scaling problem. So if you have to apply 60,000 rewrite steps in the right order, that's just a very long sequence to guess right? Even for something like ChatGPT. And I think in the natural language, there's much more variation for small errors in versions that in this like much more restricted version, like if one thing goes wrong, the entire thing breaks over. So I think there's like more lag in there. Cool. Should we close this maybe?
Any more? Then let's thank you.
Good. Thank you.
And for being brave enough to put his face on camera, both
for the recording and the video. Yeah, we thought like only using remote.
Yeah, but